All right, good afternoon and thank you for coming this session. In the previous session, Professor Chakraborty already discussed in details about the one-dimensional diffusion equation and one-dimensional convection diffusion equation, okay, how they work. So in this tutorial, I'll not give a lecture actually. I just go through those the discretization, okay, how we do the discretization, and then I'll show some example of a MATLAB code. So do you know MATLAB? Everybody knows MATLAB here? Who knows MATLAB? Can you hands up? Okay. But you can use your own language. You can use Fortran, you can use C, anything you want. You have to use your own device, all right? And from here, the one I'll show, and then I'll change a little bit, either the boundary condition or the problem a little bit, and then you have to solve it. You have to write the code, okay? And once you finish the code, show the tutors, and then based on your performance, we'll add with your your final results outcome, okay? Because we will give you the certificate. So based on, we'll collect this one. Professor Chakraborty give you some homework, that results and these results will combine together and give you the certificate, okay? So you can start here. If you can finish, that's good. We can mark you. And if you can't finish, you can go back home or you can go back to the dormitory and then finish it and show us tomorrow, okay? Now, at first, we will start with one-dimensional diffusion equation, and you know what it is. Like a one-dimensional means like a single line, okay? So we have a single line. In between somewhere, we'll give some source. Source of what? Source of either temperature or concentration or something, okay? And then we'll apply the diffusion coefficient. So based on the diffusion coefficient, it is diffused through the line. Okay, that's the thing we'll solve. It also has the analytic solution. So if you can do some validation of your numerical results, you use here with the analytical results, you will get some extra point, okay, if you can do that. So you can see the one-dimensional diffusion equation is this. So we are using the very simplified one. Professor Chakraborty showed you the general form, and we are actually giving you a very simplified one, the one we will be solving here. So this is the one-dimensional diffusion equation. Here U is a dependent variable. So which only one? It can be temperature or the concentration or anything, and D is the diffusion coefficient. So based on this D value, it will diffuse. Okay, if it is small, it diffuses less. If it is higher, it diffused higher, okay? And then the next step, what we want to do, we want to divide the domain into control volumes. So if one-dimensional is control volume and finite difference the same, okay? Is the same because it's a one line. So, so divide the domain into control volumes. So the domain is maybe L length, we just assume that L, and you have to apply the value of L in your coding. So generally we put 0 to 1, okay? So L is the length, and we can have like n control volumes, how many you want. So that is we call mesh. But mesh we call it 2-dimensional or 3-dimensional. But because it is a 1-dimensional, just point how many section you want. So the more section we have, the better results you have. So Professor Chakraborty already told you that it is a control volume. If we want to get very accurate results, we need to increase the points, okay? Because you have to interpolate. But if the point is very close, we get better results. But we have to somehow compromise sometimes. So that we will show you when you do the Ansys fluent problem tomorrow. We'll explain. But here we just focus on the one-dimensional one, okay? Now for each control volume, center is like from 1, 2, 3, 4. So we want to make center is I minus 0.5. So that is in the middle, okay? We want to put this control volume centered xi. Xi is the centered value of each control volume, okay? and then what will be the boundary of the face? So, the left face and the right face, because that called the face. Left face should be x I minus half, and the right face is x I plus half, and middle is x I. Okay, that's it. And then the width of the control volume is del x. So, this is the way we define. Now, the third one, now the integral form of the diffusion equation. Now, what is the integral form of the diffusion equation? So, if we integrate from one phase to the next phase, okay, that is from x I minus half to x I plus half. So, the left side and the right side. So, both sides we just integrate. Now, the time derivative on the left side, how you want to do? So, you know that how we do it, already Professor Chakraborty explained to you that del x del t. So, the del x, if we integrate from one phase to other phase, it becomes the capital del x. Okay? So, dx becomes capital del x, and the u, the variable, becomes the average. Okay? So, ui is the average value. So, where ui is the average value of u over the control value. Okay? And the right side is your second derivative. So, there are two derivatives there. So, we have to use the Gauss divergence theorem. I think you already know about these things. If you have any numerical any courses, so you know about it. So, how we do that? It actually convert your integral value into flux value. Okay? You see on the left side the integral value, integration from x I minus half to x I plus half, and is coming to the right side is this flux value. Okay? So, how to calculate this flux value? Upper limit and the lower limit. So, the diffusive flux on the left side. So, left side means x I minus half. Okay? So, x I minus half we just define is capital F I minus half or something, you can define whatever you like, minus the d is already there, the diffusive coefficient, and then I minus u I minus 1 divided by the length of the control value. Okay? So, minus value should be here, because its flow becomes from left to right. So, flow is going this way. So, we have to use the minus sign here. Now, the diffusive flux on the right phase, the similar I plus 1, the right phase, minus ui. So, that is and divided by del x. And now, if we want to put this together, so this the del x del t of ui is equal to, you know, the upper limit minus lower limit, right. So, you can see here when you do this one. So, from upper one x I plus half, x I minus half. So, this is the way we can just put it there. Now, if we substitute the value, we just derive f I plus half and f I minus half, we just put it here. Okay. Now, when you do the simplification, take the d divided by del x, then we are getting ui minus 1 minus 2 ui plus ui plus 1. This is the right side. Now, we just, and the time derivative, we just use this on forward difference scheme. So, this is always we do the difference scheme. Okay? We cannot do the finite volume scheme here. So, now if we substitute it together, it has become like this. Now, if we simplify, you see the ui n plus 1 the next time is equal to this. So, this is the final version. We have to solve this one. Now, we have to apply the boundary condition, okay? Because this is the main thing of CFD, because as you can see, if you want to simulate something, we have to give a proper boundary condition. For example, if you want to solve the airflow in this room, so what you have to do? We have to like find out, because the door is open, air may come from there. We have to use proper boundary condition. Maybe some heat is coming from outside, we have to give boundary condition. It is not a nature, we are not solving the nature problem, we are solving a part of the nature. So, that means the boundary we have to give proper condition, otherwise it won't be perfectly solved. Okay, that is why boundary condition is very important. when you define any problem to solve using CFD, at first you have to think about the boundary. How can you deal with the boundary? And lot of method available, it has a lot of issue with the boundary. How do we set up the boundary condition? For example, the mesh-free particle method, the lattice Boltzmann method, they have a lot of issue with the boundary. Okay? But finite volume method is the perfect one because it can handle the boundary very, very well. So what kind of boundary condition do you think we can apply to end? Because we are putting the source in the middle. Okay? So what kind of boundary condition we can put at the end? We can put, like, there are two types of boundary conditions generally we use. Professor Chakraborty already told you 3. So but we just can talk about 2. One is called I call it Dirichlet, but he pronounced differently. So Dirichlet boundary condition, that means some constant value you can apply, 1, 2, 3, 4 or something like this. Okay? And another is called Newman value, that is some flux value. For example, some wall, if it is like what I can say, some gray wall, then when it absorbs the sunlight, it can produce a heat flux. Okay? That heat flux can give us some heat, which is a rate of change of heat. Like, so this is the way you are getting. So that means you have to apply the heat flux condition. You cannot apply the constant temperature condition because of they are absorbing the heat. So here we can apply this, any one of these based on the reality. Okay? But for our tutorial problem, we will apply the constant value. But the problem will give you have to apply the flux condition. Okay? You can apply a flux condition to end. What happened you want to see. So now, and another thing is the initial condition. So how initially it was. So that is also an important thing. Because in a nature, everything is, something is happening. There is nothing called absolutely stable and absolutely nothing happening. Okay? So, but when you do some numerical simulation, you have to start with something realistically. Okay? So we assume that in a line, initially everywhere the value is the same, like a 0. We can put a 0 value. And then we are suddenly applying in the middle some source, and then we can observe what is happening. But sometimes you want to do, like, if you know what is happening inside any value, then you can apply. But this way, at the end, we can get some steady state value. The steady state value means after that solution doesn't change. Okay, that's called steady state. Now, as in your previous lecture, you found that the stability condition is very important, because here we are using explicit technique. There are 2 techniques he mentioned, right? Explicit and implicit. So we will be using explicit. And in the explicit condition, the time step is very important. Okay? So time step you have to maintain. What value of time step you need to use. So there is a number called CFL. So CFL number, that actually is a relation between the velocity, the mesh size, and the time step. This is called the CFL. Current, what is the name? Another one? CFL. Yeah. So I can't remember all the time. This is called CFL. We know the CFL. Everybody knows CFL in the CFD community. So the CFL value should be less than 1 all the time. Otherwise, your solution will not be converged. So here, so this the condition we got. For the stability condition, we have to satisfy this. Now the final discretized equation looks like this. So this the equation we have to solve. Okay, you can calculate by yourself, because this is, I skip lot of steps. So you can do by calculation by yourself, and then you can see at the end your equation looks like this, and this is the equation we will be solving. So I want to just, I think it's very too small, you cannot see it. So this is the code we put in the MATLAB online compiler. Okay, I may make some bigger. Yes. Here is the code. Okay. So what we have done, the length of the domain, you see the length of the domain is 1. I told you, you have to define how big the domain is. And then how many number of control volumes you want? 50 is too little, but I just put it here. So you can increase it 100, 200 or something. Okay. Or you can show some comparison of your results, 50, 100, 200. So that is called the mesh dependent test. We will do in our future tutorial. Okay. So how many control volumes you want? I just choose 50 here. And then the width of each control volume, the del x. Okay. The del x is L, the total length divided by how many control volume. So this is your del x, they calculate. Now D is the diffusion coefficient. I just put 0.01. You can put whatever the accurate value is. Okay. And then dt is the time step. For explicit method, time step size will be very, very small. Okay. So that's why I put 0.0001. And now how long we want to simulate it? Just 0.1. Okay. 0.1. Now this is the how many time step we can easily calculate t, okay, total time divided by the time step. So this is the number of time step. This is the how many number of time step we want to run. Okay, that's it. This is the we just define this way, and now we have to initialize the system at first. So u we put 0. Well, the source term, it can be, as I said, it can be temperature or it can be concentration or anything. We just put, okay, we just put zeros. Initial condition is 0 in every x. Okay, it is 0. Now the new one, we just put it there as it is. So because we need it later on, and x is the cell center. So we define the center. Okay, so I just told you that how to get the cell center. 0.5, okay, minus this one. This is the way we just define. Now the initial condition for Gaussian pulse, how we apply? We apply like a bell shape. Okay, this is our initial, the source term, as I said. Source term we want to put in the middle because it is 50, right? So 25th position in the middle. We want to put some bell shape curve and then apply the diffusion coefficient, and also a diffusion coefficient we want to see how it is moving. Now the boundary condition, as I said, u1, the left boundary is 0 and u at the end boundary is 0. That the Dirichlet condition I put, and you have to use the Newman condition, some flux condition. Okay. Now, so this is the two value. I just define the stability condition. We just split it, and then we just see that if it more than 0.5, then will give us some error, and the message will be stability condition violated. And then we have to reduce this value. So yes, sir, reduce dt or increase dx. So this is the message we will get if it doesn't work. So this condition gone. Now we have to make some plotting. So this is the plot. I think if you want to use any other C or anything, any code, so you can write this on. So here they will plot this value. This is the variable against x. Okay, and then the time stepping loop. So use from n from 1 to nt. Nt we already put 0.1, and then a loop over interior control volumes, and this is the value. Okay, we just split it up, the flux, okay, and two fluxes left and right, and then we combine together here. But you can directly use the equation, the final equation you saw. You can directly use it, or you can split it here. So, it is easy to understand. If you have any mistake, you can find from here. Okay? Or if you want to only calculate the left flux how much it is, or the right flux how much it is, then you can is better way to do that. So, now your u nu here is storing as u, and then this is the boundary condition is there. Now, it's finally they are just plotting here. So, now if you run this one, should work. What happened? Line on column 13. There is a percentage here. Yes, you can see here we applied here, then it is actually diffusing. How it is diffusing? Okay. So, you put the value here, now it diffused, you go up there, and also, so this is the blue line. So, this is the diffused. The blue line is the initial value, and then they just diffuse it. All right. So, this is the condition we did for one dimensional diffusion equation. So, do I tell them to do it, or just do the second one as well and then tell them to do it? What do you think? Second one. All right. So, this here, and now I am going to the one dimensional convection I think is all right. I can use directly. Yes. So, it is most of the places the same, the similar. It has only one extra term is the convection term here, u del x. This is the extra convection term. Okay. So, this convection term we have to discretize. Now, you can see u is the dependent variable, it's concentration or temperature, v is the convection velocity, and d is the diffusion coefficient. So, as before, the length is L, we will divide it into n control volumes, and the center of the control volume center xi, which is I minus 0.5 del x, and each control volume has a boundary. As I said, the left one is xi minus half and the right one is xi plus half, and the bottom one is the same thing. We just did the integration from the left face to the right face, I minus half to I plus half, the time dependent term, the convection term or advection term, and the diffusion term on the right side. Okay. So, now one by one we have to discretize. So, the time derivative term exactly same as before what we did, like the differencing scheme. So, use the forward difference in time. So, del u I del t is equal to this one. Now, the convection term. So, this is different, we did not do it yet. So, the here we apply the divergence theorem. Okay. So, in this divergence theorem, when you do the integration in terms of x, then we are keeping v as a constant, okay, and then we are making the difference form, okay, del u del x. Now, to compute this one to that one as a upwind scheme for stability, we have to do it ui minus half is equal to, just call it ui, okay, and ui minus half is I minus half. So, just making it. So, it is possible. So, indices we can change the indices in the code, that is not a problem when the v is greater than 0. So, now if we substitute here, it is coming v into ui minus ui minus 1. Now, the diffusion term, it is very much similar what we did last time, just d ui plus 1 minus 2 ui plus ui minus 1 divided by del x square. So, we did it differently, but you can do the same way, okay, but at the end you will get it. Now, combine these three together is coming this. Okay. Now, if we do the simplification ui n plus 1, we are getting this whole value. Now, for here we have two stability condition. The CFL, I told you before, the CFL condition for convection is, you see the velocity, time step and the control volume length. Okay. So, these three are very correlated and it should be less than or equal to 1. Okay. So, whenever you make, you can make, if you make like you can see here del x, if the del x is small, then the whole system is becoming bigger, right, and if the delta t is bigger, whole system is becoming bigger. So, that means you have to readjust when you do meshing and time stepping. Okay. So, for implicit technique does not matter, for implicit one it is not a problem, but if you want to solve explicitly, then the problem is you have to always calculate it. Okay. What is the length of the control volume and what is your time step and the velocity, and then you have to multiply and get the value, it must be less than or equal to 1. You have to calculate beforehand, otherwise your solution will diverge. Now, the stability condition for diffusion is this one, we got it before. So, now again we apply the boundary condition, the similar things we can apply, as this is the final form of the discretization equation. Now, we want to, we have again another example of here the same, the length is 1, okay, and how many control volumes we want, just 50, and then width of the each control volume is L by Nx. Okay. So, that means 1 by 50, and then the diffusion coefficient again we use 0.01, you can vary it and you can see how the results actually change with this, and the convection velocity. Okay. So, what is the convection velocity? That means if we apply some concentration or temperature in the middle and then there is some velocity is going on and convecting away. So, then we can see how this concentration or the temperature is moving. Okay. So, now the initialization of the solution. So, we are putting u is equal to 0 initially, and then we are putting some like a placeholder we are just defining before, and then this is the cell center we use, and now this is the Gaussian pulse we apply in the middle. Okay. So, this is actually the source. Now, the boundary condition we again use the Dirichlet condition, and on the left one and the right one we put both zeros, and these two values, and then we check the stability. We told that if alpha is greater than 0.5 and beta is greater than 1, okay, we just call it alpha and beta, but whatever you can tell. And then if the error is present, then they can give us the message stability condition violated. okay, reduce the delta t or increase the dx. Now, this is the plotting again for the last time, and now we are using the time stepping. So, there are two loops, and here we just use the flux on the left, flux on the right, and for the convective flux we have two, right, one, and this is one, the upwind one, and here, and the net flux is this here, and we are updating the solution up to here. Okay. So, now apply the boundary condition, the similar boundary condition again, and at the end we are plotting it. And now we want to run this one. So, if you like to have this code, they can share with you. So, you can have it, and then just write you the code by yourself. You see here, the initially the pulse was this, and then the convection it moved away until here. So, this is the final one. All right. So, now I think now it is time to do some practice. Write the code by yourself, and then we will just invigilate, and if you have any question you can ask. They will also help you, and I will also be here. So, if you have any question you can help. Okay. But you have to apply the flux condition at the end, not the just a value 0 or something. Just put some flux condition of the u. Okay. Are you sharing? So, everybody has computer with you? Or you can write the code on the paper and then you can type in the computer. And also for tomorrow, when you do the CFD using Ansys, because we will be doing Ansys, but you are free to use any software, COMSOL or anything. I also know COMSOL, but that is your own. You can use it, but we will be showing here only the Ansys Fluent. So, the student version of the Ansys Fluent is free.
We are calculating like this. We know the solution of these points because these are the grid points. So, del u by del x of E, we can write it like this. By using central difference. So, that is written in the code.
Try to read the number of points and also coefficient. Just play with it. Okay, change some parameters and try to understand the effect.
So, in the solution you will see in the diffusion problem there is no directionality. So, basically this wave will just diffuse out, but in case of convection the pulse will migrate towards the convection velocity. In the solution you can see. So, try to run both the codes and see me.
Change the parameter. check the results, how it is changing. You can copy the result, you put somewhere in your Word file or something, and then you compare. Okay? Or PowerPoint.
Sir, boundary condition, what next we should give?
Yeah, that's what I'm asking. So what kind of boundary flux condition we should use?
Actually for Gaussian pulse, both the ends are fixed only.
Yeah.
So
we have to give some hot condition.
We can give the, we can ask them to change the convection velocity and plot, compare the two.
I think that's a good idea. Convection velocity. And compare together.
Yes.
So instead of 1, put them 0.5 and 1.5 or 2 and see the results. Write it down what you need to do. Continue. Which one?
কোয়েশ্চেনটা ডিসপ্লে করতে বলছে।
We did not write any questions. Just we are modifying this.
Just ওই ইকুয়েশনটা।
Okay. So the first one is, this is the final one.
The final one is কোয়েশ্চেনটা মেইন ইকুয়েশনটা।
Okay. All right, so your task will be change the convection velocity. Just keep the zero condition both sides. Just use the Dirichlet condition. Change the convection velocity. The one I use 1. Now it change it. Okay, and then copy the figure and put in a Word file or the PowerPoint file. Okay, and after it change, get another figure, put side by side and see the change, how it is changing. That is one. And another one is change the diffusion parameter. The diffusion parameter I put 0.01. The change this parameter and observe the results. And also compare your results in a Word file or in a PowerPoint and show the difference. Okay. Once you can do that, fantastic. Yes.
The Gaussian pulse taken for easy visualization purpose, initial condition.
Yeah.
Gaussian pulse was taken. Is it taken for easy visualization?
No, they apply the source, how it is applying initially, and then we just apply.
No, instead of Gaussian
Initial
pulse,
condition.
we can give
Anything, you can put like a straight line or something, and then how it move, that's what you want to see. Do you have their attendance sheet or something? Once they finish, just take it, they have done, so your mark will be taken here. So there are two problems here. You have to copy one by one. Yeah.
Sir, instead of Gaussian pulse, what other functions can we give any waves in or something? Does it have to be compatible?
Yeah, that's what I'm thinking. You can give. So it is better to see that, but maybe along a line, only straight line. Put some source along a straight line, vertical line, and put the sub value u value, and then the v is destroying it. So maybe it will be bent, something like that. You can also do that. Yeah. You can change the shape of the Gaussian one. You can change this parameter and see how it looks like. Yeah, you can play with it. Oh yeah, it's increasing up to 5.8 or something. And then it's coming down. Trying to choose too much. Okay, good results. So this is only the diffusion coefficient which now see the other one. Oh, sensitive. Yeah, that's the reason.
You also try to print the results for 5 intermediate time steps. Yes. Sorry? No, you don't have to increase the total time. You have to print the results for 5 intermediate time steps. আচ্ছা আচ্ছা ওই ভ্যালুগুলো
results of 5 intermediate time steps মানে 0 on 1 এর বদলে 0.1 এরকম
নর্মালি কি একটা স্টার্টিং আর আরেকটা তুমি এন্ডিং এর পাচ্ছ, মাঝের টাইম স্টেপগুলো তো কেমন হচ্ছে ওটা P minus U of W, but these value are not known because these are the grid points, these are not the grid points, these are the grid points. So for this we are taking that upwinding scheme. So what we are telling that if convection velocity is there, so there is a predominant directionality of convection. So to calculate the velocity at this phase, the value will be affected by both these two. If there is no there is no convection term, if there is diffusion has no directionality, so it will be both affected by these two, we can average. But as there is a predominant direction of convection, so we can assume that this value will be maximum, affected mostly by this value. So this UW we are approximating as U capital W, and for this similarly for U of small e we are approximating is U P. You can see in the code. So this is the upwinding scheme, because this value we know at the grid points we are solving. If V is if this convection velocity is negative, then in the scheme you have to update like this. This UE velocity, the velocity of at the phase UE will be mostly affected by this point now. So this UE will be
accordingly it will change.
Yeah, if this is yeah, you have to check.
Yes, for the first code there is a variable called flux. There are two variables called flux left and flux right. So there you have minus D and the term, so that will be plus D in the first code. Did you find flux left and flux right? So that will be, instead of minus D it will be plus D. And for the second code you have flux diff left and flux diff right. So in that also it will be plus D instead of minus D.
You don't need to reduce the result is okay, because we are just testing.